Hi, everyone. Welcome to Math for Biologists. And hey, it's Foxtober. All right, let's talk about making reagent solutions. We're not going to really talk about buffers too much today, but we are going to talk about complex solutions used in biotechnology, right? That's what we do. So we need to do some math, and you don't have to have a math brain to do math, especially not for biology, where most of these processes you can use your logic to help you figure out if you're doing it correctly. So I'm going to show you some of the common ways we calculate for reagents, solutions. We're not going to talk about the buffer thing again, but common solutions that are always used in labs. You have to make them. Generally, no one's going to hand you stuff. Maybe when you first start, maybe if you're a technician, but in general, you need to be able to make some reagents and solutions. Almost every single kit, every protocol requires you to do some dilutions. And I know the word dilutions is scary. We're not going to do serial dilutions. We're just going to do dilutions based on our M1 V1 equals M2 V2. We're going to show you how that works. We're going to talk about if you have more than one reagent in a solution. We're going to talk about molarity. Woo! Chemistry. Ah! It's going to be fine, I swear. All right, so we need to know stuff to do biology in the lab. Let's see what we have. Let's start with molar solutions. Let's try to remember some chemistry. So we need to make a reagent, and in order to figure stuff out, you need to know what you're going for. What is your final concentration and what volume do you want? That way you can set up your equation. So remember, if you're starting with something solid or a crystal or powdered, right, we need the molecular weight, and you're not going to ever know what those are, so you need to look it up, right? If you're not given it on the, if you have a reagent in a bottle, it'll generally give you the molecular weight on it. If you have something in a liquid, then you need its molar concentration, 1 molar, 2 molar, or its density and molecular weight, which we're not going to worry about that. We need to know total volume and the concentration, like I said. Okay, so we need to set up our equation using moles per liter times the molecular weight times the volume. Okay, that gives you grams. Wait a minute, what the heck does that mean? Okay, so let's just break that down a little bit. So if you want 1 liter, that's what your final volume is. If a 1 molar solution of sodium chloride, and in this case your sodium chloride, they give you the molecular weight right there. What is molecular weight? What units? We always carry our units, and you're going to see that these instructions, which I didn't make, I just adapted them, don't always carry units, and it's confusing, especially for biologists. If we can follow the logic, we can do the math. So molecular weight is always in grams per mole. Okay, so 58 grams per mole. We're going to carry our units, and so they're showing us what's 1 molar. That's 1 mole in 1 liter, right? What's 2 molar? 2 moles in 1 liter, etc. Okay, so 1 molar, right? Here we are, 1 mole per liter. So 1 mole per liter, because we want a 1 molar solution, times molecular weight. Here we go, moles per liter, multiplied by the molecular weight, right? And then the volume needed. Do the math, 1 mole, 58 grams. We want 58 grams in what? 1 liter. We need to have, right, 58 grams of NaCl and then we put it in a flask and we add up to 1 liter. Remember, even powdered stuff, solid stuff, in this case crystal stuff, takes up space and volume. So you don't want to measure out 1 liter and pour it into your weighed out 58 grams of sodium chloride. You want to put the water with the sodium chloride up to 1 liter in some sort of volumetric flask, otherwise known as a graduated cylinder, right? And you want to stir and make sure it's all mixed up really nicely. Okay. So again, we just need to know, right, 58 grams per mole in 1 liter, right? Because 1 mole in 1 liter. All right. Yes? No? Yes. Okay, what if we take another example and show it a little bit differently? Maybe that will help us so we can apply what we've learned. So we want 1 liter again, and we want 0.5 moles potassium chloride. Okay, so molarity is the number of moles of your solute in your volume, which is generally liters, right? Okay, so first we have to find the molar mass of potassium chloride. If we have potassium and chloride, then we can figure out what their molecular weight is. So molar mass, molecular weight, same thing. So if potassium is 39.1 grams per mole, chloride 35.45 grams per mole, potassium chloride is 75.55 grams per mole. Okay, so we want to prepare a 1 liter solution of a 0.5 molar solution. Okay, so mass of solute equals solution volume times molarity times molar mass. Okay, so essentially same formula that we used on the previous page, right? So what do we need? We want 1 liter, right? So here's our 1 liter times multiplied by 0.5 molar, right? Which is, what is molar? Sorry, moles per liter. It's hard to write small moles per liter. Times 50, times 74.55 grams per mole equals what? Okay, so if we want to go and actually do our math, right, we know 1 times anything is that anything. So that just goes to right here, right, just goes to 0.5. And we see our liters cancel. And we're left here just with moles, right? See how that works, carrying your units? And then we multiply that by the molecular weight, right? So we had liters times molarity times molecular weight. It tells us how much we need. So times that guy equals grams. So how are we left with just grams? What happened to our mole? What happened to our units? Well, looky here, the mole here, right? And the mole there cancel because they're on top of each other. It's like a 1 and a 1 on top of each other, gone. And we are left with grams. So now we know we need 37.28 grams potassium chloride. And so that's how much we would put. What do we put it in? That goes into 1 liter of water, right? We put the solid in first, dump the water up to 1 liter, and that would give us a 0.5 molar solution. And so you could do the math to make sure that actually works, right? So if you have 37.3 grams divided by, what is the 74? That's grams per mole, right? Equals what? How many moles? So again, if we're dividing, right, they're using the divided by symbol, that ends up, right, we have to flip this guy, and then guess who cancels? Our grams, and we're left with 0.5 moles. Is that what we want? Yes. 0.5 moles in 1 liter equals 0.5 molar. So we checked our work forwards and backwards to make sure we got what we were looking for. Molarity. Live it, learn it, love it. What else do we have here for you people?